Hello viewers on YouTube. In this video tutorial, we are going to learn how to figure out the stationary points and value of a multivariate functions. So without any further ado, let's get started. So the first thing you have to be familiar with is the conditions that has to be satisfied before a particular point, which we call the critical point, could be any of the following stationary points. So the stationary points include the minimum, we have the maximum, and we have the saddle points. Before you can now pay attention to identifying which of these is the stationary point, you must know how to find what we call the critical point. To find the critical point, you basically need to find the partial derivative of that function, of that multivariate function. So let's say we have a function of z to be equal to a function of x, y. Z is a function, is a multivariate function of x and y. So to get the critical points, you basically need to find the partial derivative of z with respect to x and set to be equal to 0. Then you also find the partial derivative of z with respect to y, likewise set to be 0. Then having done that, you can now solve the two equations simultaneously. At the end of the day, you get the value for x and y. Whatever value of x and y you got is your critical point. Now, the critical point will now be any of these three. So it could be minimum, maximum, or saddle. So now to not fail, which is going to be, then the conditions we have also stated must be satisfied. Okay, respectively. So now, when will the critical point be a minimum point? It will be a minimum point if z of x times z of y minus z of xy all squared is greater than 0, and z of xx is greater than 0, likewise z of y is greater than 0. So what does this mean? It means having gotten your critical points, you will now take the partial derivative of z of x again second time. I'm complicating. Then you take the second partial derivative of that function z with respect to x. Then you also do it for y. Then having done that, you multiply them. Then you subtract the cos partial derivative of z with respect to x and y respectively, and then square it. You do the math and see if your result is actually greater than 0, then the first part of this part has been satisfied. Then for the second one is that z of x must be more than 0, likewise z of y. By the time we begin examples, you will see what I'm saying next time. But make sure you have all these conditions written down for reference. Now, for maximum, this is the condition. It's similar to this, but with just slight changes. See, the product of the pure partial derivative of z with respect to x and y minus the square of the cos second partial derivative must be greater than 0. But now, z of xx will be less than 0, and z of y would also be less than 0. So if this all take place, then you just need to know that your critical point is a maximum point. Now for saddle points, it's straightforward. Z of xx multiplied by z of y minus z of xy all squared must be less than 0. So you don't really need to test for this one. So far you realize that this is already less than 0, then you can conclude that it's a saddle point. Usually for saddle points, z of xx and z of y always alternate. If one is more than 0, the other one will be less than 0. But this is the most important condition for saddle points. Now, in a case which is very rare, is if this expression at the left hand side is equal to 0. In this case, then the stationary point is indeterminate, and so we can't really justify what the stationary point is. Am I complicated? So let's try to go over some examples and then let's put all these into good use. Keep in mind, critical point, then stationary point. If the question asks you to find the stationary point, you need the critical point to tell the stationary point. But the question actually is specific in such a way that it says you find the critical point, then you don't need to go through all these completions for you to get your answer. The answer is just whatever values of x and y you got upon solving these equations simultaneously. So, example number 1. So the question says that investigate the stationary values of the function. So the function is as follows: z equals to x squared plus xy plus y all squared plus 5x and minus 5y plus 3. So this is the question. So we are required to investigate the stationary value. Now you might be wondering, all I've said earlier was about points, but this problem is actually asking for value. So in that case, what are you to do in that sense? Well, if the question says ask for value, we still need the points. So why don't we find the point first? And then after that, we can now see the values. So let's find the points. Before we could find the stationary point, we need the critical points. And to get the critical point, we need the first partial derivative of z with respect to x and the first partial derivative of z with respect to y. So what actually is z sub x? So that's simply 2x. When we differentiate these with respect to x, you have 2x, then plus. Now this is xy, but we are doing partial differentiation. So y will must be taken as a constant. So differentiating x with respect to x is 1, and when we multiply with y, we have y. This is 0 as a constant. This is 5, so we have plus 5. This entire expression is 0, as they will be considered as a constant. Now, what about z sub y? For z sub y, let me put it on right anyway. Z sub y would simply be, so let's pay attention to this, because this will be 0. It's a constant. So if we differentiate xy, or we differentiate y with respect to y, treating x as a constant, yeah, then we would have x. Now differentiating y squared, we have 2y. Perfect. And finally, this and this will be 0 as a constant. Then paying attention to minus 5y and differentiating that, we'll have minus 5. Now since we are required to set z sub x and z sub y to 0, at the end of the day, then we should end up with 2x plus y plus 5 equals 0. X plus 2y minus 5 equals 0. Perfect. So right now, we basically need to solve these two equations simultaneously. But before we do that, let's separate constant from variables. From this equation 1, we subtract 5 from both sides, and we end up with 2x plus y equals minus 5. So for the second one, we had 5 to both sides, and then we have x plus 2y equals to 5. To solve this simultaneously, let's consider using elimination method. Now to use elimination method, we basically need to make one of the variables that we are going to cancel. We need to make their coefficient the same. So basically, let me try to eliminate x. Thus, I need to multiply the second equation by 2, so its coefficient can balance with that of its coefficients in equation 1. So let this be 1, let this be 2. Perfect. So multiplying equation 2 by 2, equation 2 multiplied by 2. Then we should have 2x plus y equals minus 5 and 2x plus 2 times 2y. Sorry, yes, 2 times 2y, that's 4y equals to 2 times 5. That's simply 4. So now we can subtract 2x minus 2x. That's simply 0. Now plus y minus plus 4y. Be careful. That will be minus 3y. We have positive y, the minus plus 4y. That's not t plus. Now this negative effect, which end up with plus y minus 4y. And doing this math, the result is minus 3y. So right now, we have an equal sign. Minus 5 minus 10. It is like plus 10. So minus 5 minus plus 10 is simply minus 15. And right now, we can divide through by 3 or minus 3. Then y should be minus 15 divided by minus 3, which is 5. So that's the value of y. And having gotten y, we can actually put it back right in equation 1. Now to get the value of x. So put y equals 5 in 1. Thus, in equation 1, which is this, we will have 2x plus y is 5 plus 5 plus 5 equals 0. Adding this up, we have plus 10. Then we should have 2x plus 10 equals 0. Then proceeding forward, x should be minus 10 by 2, which is minus 5. So thus, our critical point, let me just have that C, simply x value come first. You can see it's been expressed in coordinate form. We express it in coordinate form. And in coordinate form, x value has to come first. So we have our x, which is minus 5, and followed by our y, which is 5. You can close the bracket. Perfect. Now that we have the critical point, we can now fill the stationary point. So let's jump to step 2. So this can actually go. Likewise this. For step 2, which we use to fill the stationary point, we need, and have it in white, we need z sub xx, the second partial derivative of the function z with respect to x. Likewise, the second pure partial derivative of the function z with respect to y, and the second cross partial derivative. So now, z sub x is this. And what would be z sub xx? It implies that z sub xx would be what? Well, this is y and this is 5. They will be considered as a constant. Thus, we need to pay attention to 2x. The derivative of 2x with respect to x is simply 2. And that gives z sub xx. Now, for z sub yy, what would that be? This is x, and this is minus 5. So they must be considered as a constant. So it means we need to pay attention to 2y. Differentiating 2y with respect to y, we have 2. Thus, we have our z sub y. Now, something just popped up my mind now. For those who may be confused, z sub x is the same as di z di x. And for z sub y, we have di z di y. And for the second partial derivative, which is z sub xx, that's di z square z di x squared. Then you have it for z sub y as well. And for the cos z sub xy, that's di square z di x di y. And if y comes first before x, you have to follow that order for this one as well. So I think I just need to clarify that. For those who might be like, why am I using z sub x, z sub y? This is much more better to write, and it's more flexible, so I prefer using it. Now let's confirm the conditions. So we need to first of all confirm that the product of z sub x, x, and z sub y, y minus the square of the cross product z sub x, y is greater than 0. If this is confirmed, if this is satisfied, then it means the critical point can never be a saddle point. You understand? So it would rather be a minimum or a maximum. So let's confirm that. Now, z sub x is 2 multiplied by z sub y is also 2 minus, my bad, we are here to find the cross product, second partial derivative. Cross partial derivative. Now keep in mind, either you do z sub xy or z sub yx, you should end up with the same result so far the function is continuous. So usually they are the same. So regardless, you should be on the safe side. So let's just keep on using z sub xy for this video. So what would be z sub xy? We have z sub x already. So basically we will now partially differentiate this z sub x, but now with respect to y. So let me have that in mind. Z sub xy will now be equal to, now we would treat this as a constant. Why is this? So those will be 0. We would instead pay attention to plus y because we are now differentiating partially with respect to y, and the derivative of y with respect to y is simply 1. This means z sub xy is simply 1. So minus 1 squared. So is our result greater than 0? 4 minus 1 is equal to 3. Since 3 is indeed more than 0, thus the first condition is satisfied. Hence, the critical point minus 5,5 is not a saddle point, but instead would rather be a maximum or a minimum point. Now, let's confirm which exactly is it, maximum or minimum. For which now know, keep in mind, for it to be minimum, z sub x must be more than 0, z sub y must also be more than 0. Well, with the results we have, we actually don't need to do anything else. Clearly, 2 is more than 0. Thus, final justification is that the critical point minus 5.5 is the minimum point. But as you can clearly see, z sub x is actually 2, z sub y is also 2, and this result is more than 0. Hence, the first condition is satisfied. So the condition for minimum point is satisfied. So therefore, our critical point minus 5.5 is a minimum point. So guys, this is how you can easily tell the stationary point of any given multivariate function. This is how you find this helpful understanding. Let's consider more of few examples to understand the concept to full potential. Example number 2. So, the question number 2 says that determine the stationary values of the following function, and the function is as follows. Oh, the previous example also asks us to find the stationary value. My bad. Let me write the question back. We have z to be x squared plus, please, we are going back to the example number 1. We are yet to complete it entirely. We actually found the stationary point, but we need the value. So let me write it back. It is x squared plus xy plus y squared plus 5x minus 5y plus 3. Now, the critical point is minus 5,5, and we confirmed that it is a minimum point. Now, we need the minimum value, which is the stationary value. So to get this, we now take these two values. Remember, the first one is for x, and the second one is for y. We now put it right here. Wherever you see x, then you put whatever it is. Wherever you see y, put whatever it is. And with that, you have your stationary value. So our stationary value, which corresponds to our minimum value, would be, okay, then let's express it in a more generalizable form. Let it be z of minus 5, 5. So that will be minus 5 all squared. Okay, perfect. Plus, we have minus 5 times 5, and plus 5 squared. Alright, plus 5 times minus 5. Okay, minus 5 times 5 plus 3. So this is indeed equal to minus 5 squared is 25. Then plus minus 5 times 5 is minus 25. 5 squared is 25. 5 times minus 5 is minus 25. Minus 5 times 5 is minus 25. 5 to 5. Minus 25. Minus 25 plus 3. So this go. This also go. Minus 25 plus 3 is minus 22. So minimum value is minus 22. And yes, we have the final answer. So that's it, guys. You have the point, put it in the function, and you have the value. That's it. Now let's continue with our second example number 2. So we are also required to determine the stationary value, but now with a different function, and the function is as follows. So we have z to 5xy minus 4x squared minus y squared. Then we have minus 2x minus y plus 5 plus 5. So that is the problem. So we want to determine the stationary value. Well, to find the stationary value, we need the stationary point. And to get the stationary point, we need the critical point. And to get the critical point, we need to partially differentiate the function with respect to x and y respectively. So what actually is z of x? So now, let's treat y as a constant and pay attention to 5x. And if you want, you can treat 5y as a constant and pay attention to x. Either way is perfect. So differentiating x with respect to x is 1, and we multiply with 5y, we should have 5y. And the derivative of 4x squared with respect to x is minus 8x. This is gone, constant. This 2 is also gone, constant. The derivative of minus 2x with respect to x is minus 2. Thus, we have our z of x. Now, for z of y, we treat 5x as a constant and differentiate y with respect to y. And that gives us 5x. This is constant, 0. Derivative of negative y squared is minus 2y. Constant, 0. Derivative of y or minus y is simply minus 1. And this is also gone at 0. Now we have the two of them. We need to set each of them to the 0. Thus, we have 5y minus 8x minus 2 to the 0 and 5x minus 2y minus 1 to the 0. So just like before, let's separate variables from constant. Now, the variables in this equation are not actually in order. So in the process of separating variables from constant, I would also make sure the variables are in order. So what I'm saying in sense is that x would be in line, y would also be in line. So thus for equation 1 we should have, if y is coming first, let x come first minus 8x plus 5y equals to 2. Then we have 5x minus 2y equals to 1. So basically, the minus 2 has actually been taken to the side and it becomes positive 2. And I change the position of minus 8x and let it come first. Since it's not going across the equal sign, the sign remains unchanged, then this is like plus y But that's why we have that plus y right here. And nothing was actually done here other than sticking the minus 1 to the side. And doing that, we have plus 1. So everything is online and perfect. So just like before, we can now try to eliminate one of the variables in order to get the other one. So let's get rid of x. So basically, for that to be possible, we need to make the coefficient the same. But the values are quite large, so it's better we get rid of y. But let's still get rid of x. Okay, I don't want to be switching. So to make the equation the same, we need to multiply equation 1 with the coefficient of x here, and equation 2 with the coefficient of x here. So multiplying equation 1 by 5 and equation 2 by minus 8, we have it to be minus 8x times 5 is minus 40x, and 5 times 5 is simply plus 25y equals to 10 by the time you do 2 times 5. Perfect. Now keep in mind, times 5 doesn't mean 2 times 5 alone. When you multiply each term in that equation by whatever you are trying to multiply with it. Okay? Yes. 5x times minus 8 is minus 40x. Minus 2y times minus 8 is positive 16y. And 1 times minus 8 is simply minus 8. So, what should we do? Subtract. Equation 1, let's say 1 minus 2. Yeah. 1 minus 2. So, minus 40 minus 40 is 0. Clearly, this turn this one to positive and we cancel that. Plus 25y minus plus 16y is the same as plus 25y minus 16y. Now gives us 9y equals plus 10 minus 8. That becomes plus 10 plus 8, which is 18. And dividing through by 9, y should be equal to 2. By the time you divide through by 9, 18 by 9 is simply 2. And that's the value of y. So just like before, let's put y equals 2 in equation 1. So put y equals 2 in equation 1. Then we have minus 8x plus, instead of 5y, 5 times 2, that's 10. 5 times 2, 10. And we replace y with 2, please. And that's equal to 2. Now subtracting 10 from both sides, minus 8x. Would be 2 minus 10, which is minus 8. Dividing through by minus 8. X should be equals to 1. So our critical point is simply 1, 2. And that's it for this problem. Now that we have the critical points, let's pay attention to the stationary points. From there, we can have our stationary value. So, to find the stationary points, we need some of these conditions to be satisfied. So first, we need the second pure partial derivative of z with respect to x, and the second partial derivative of z with respect to y. And likewise, the cross partial derivative of z with respect to x and y. So what actually will be z sub xx? Well, we need to take this and this as a constant, and then differentiate the same with respect to x, which is minus 8. And for z sub yy, take this and this as a constant, and differentiate this one with respect to y, and that's simply minus 2. And for z sub xy, we have to take this and this as a constant. Pay attention to this one and differentiate it with respect to y. That will give us 5. Please, I hope you are following. Perfect. So having gotten all this, let's now see if the product of z sub xx and z sub yy minus the square of z sub xy is more than 0. If it is less than 0, then it is saddle point. But if it is more than 0, then it would either be minimum or maximum. So z of x is minus 8 times z of y is minus 2 minus z of xy is 5 all squared. So minus 8 times minus 2 is indeed equal to 16. Minus 5 squared is 25. 16 minus 5 is minus 9. Well, unfortunately, minus 9 is not more than 0, but instead less than 0. Thus, we don't need the second condition. This is enough for us to confirm that the critical point the critical point 1, 2 is a saddle point. And to get its value, we need to put it right here. So the saddle value would be z of 1, 2, and that would be 5 times 1 times 2 minus 4 times 1 all squared minus 2 squared. Okay, then minus 2 times 1 minus 2 plus 5. Clearly, this will cancel this one. No, they won't. Let's simplify. Okay, let's simplify so that you don't get lost, and also to avoid silly mistakes. Alright, so this clearly means that z of 1, 2 will now be 5 times 1 times 2 is 10. For 1 squared is still 1, then we have minus 4. 2 squared is 4, then we have minus 4 again. 2 times 1 minus 2. And this like minus 2 plus 5. That's just plus 3. Perfect. So let's add this up. So minus 4 minus 8 minus 2 minus 10. So 10 minus 10 plus 3. That's number 3. So this is our saddle value. And the saddle point is 1, 2. So guys, this is how you can easily find the stationary point of any given multivariate functions. Hope you find this helpful and understandable. Thanks for watching. See you in the next video. If you are yet to subscribe, feel free to subscribe to this channel. And also don't forget to leave a like if you enjoyed the video, so YouTube can recommend it to many audience out there. Thanks for watching once again. Bye for now. So this is the exercise I have for you. Feel free to share your solution with me via the comment section below. So consider finding the stationary point or stationary value of the given function. Z equals 3x squared minus xy plus 2y all squared and minus 4x minus 7y plus 5. So that's it. Thank you once again. Bye for now.